So I want to calculate the flux across the back surface here. So I've drawn in that back surface. It's going to be a rectangle of exactly the same size as the front surface, so its dimensions are delta y and delta z, but it's in the very back. So along this back surface, if I want the normal vector to be pointing away from the enclosed volume, my normal vector has to be pointing straight back. So now my normal vector is going to be negative 1, 0, 0. So the normal vector to the front surface was pointing straight forward. That was I, or 1, 0, 0. The normal surface to the back surface is pointing straight back, so that's negative I, or negative 1, 0, 0. Okay. So I'm trying to calculate the double integral along, I'm just calling it S sub b for the back, okay, of f dotted with n ds. We've determined that n is constant. I'm going to do something similar to what I did along the front surface, which is I'm going to approximate this. Again, this is what makes this an informal argument rather than a formal proof. Okay. I'm going to approximate this by saying this is eventually going to be small. I know that the value of f, my vector field, may vary at points over this surface. That's rather inconvenient, so I'm going to do what I do anytime I'm creating a Riemann sum, which is go into denial and just pretend it's constant. But I'm not going to bother chopping this up into little pieces because I'm assuming that these pieces are small and shrinking to 0 anyway. So I'm just going to approximate this by looking at what happens at that center point. But that center point, that would be directly behind P naught here. Remember we said P naught was X naught, Y naught, Z naught. So if I go straight back from the center of the box to the center of the back, I'm not changing Y or Z. So there's still going to be Y naught and Z naught, but the X value has changed because it's no longer X naught, I've moved back a little bit. And it's actually just going to be X naught minus delta X over 2. Because delta X is the full distance between the back and the front, so half of that distance will be the distance between the center and the back. Okay, so I'm going to approximate this with the double integral over the back surface of f evaluated at x naught minus delta x over 2 y naught z naught, dotted with the normal vector. This is not an approximation, that's exactly this. And then we're going to integrate that with respect to s. But again, what this is going to do is I know my vector field f has 3 components, right? It's got, I've ceased to write it down, but it's got f, g, and h are the component functions. So this right here would be f, the first component, evaluated at x naught minus delta x over 2, y naught, z naught, comma, g, the second component function, evaluated at this point, comma, h, evaluated at x naught minus delta x over 2, y naught, z naught, oh my goodness, I'm running out of space, dotted with, I'm just going to continue this down here because I'm running out of space, dotted with negative 1, 0, 0, and then integrating ds. But of course, if I work out that dot product, these 2 zeros are just going to kill off those second 2 component functions. So this is the double integral along the back of f at x naught minus delta x over 2, y naught, z naught. I'm sorry, negative, because I'm dotting with a negative 1. Okay, so negative f evaluated at that ds. But again, because I've approximated with a constant value, that is constant. So I'm just going to get this constant times the area of the back surface, but that's negative f at x naught minus delta x over 2, y naught, z naught, times delta y, delta z. Okay. All right, let's see. So I'm going to add that in up here. This should actually be an approximation sign up here, not an equal sign. I apologize, I had miswritten that as an equal sign. But now we're saying along the back, it's approximately the opposite of f at x naught minus delta x over 2 y naught z naught times delta y delta z. Okay, so far so good. Okay. Now, if I were to calculate the flux density, okay, so if I were actually to calculate the limit as delta x, delta y, delta z goes to 0, 0, 0, okay, of the double integral along S of f dotted with n ds, that's the flux, divided by the volume, which is delta x, delta y, delta z. I know that this would be the limit as delta x, delta y, delta z goes to 0, 0, 0 of, basically this would become 6 integrals. Front plus back, top plus bottom, left plus right. Okay, they're all being divided by the volume. I'm just basically breaking that up into 3 parts. So I'm going to say this is the double integral over the front surface of f dotted with n ds plus the double integral along the back surface of f dotted with n ds. All of that over delta x, delta y, delta z, plus, and then I would have the limit as delta x, delta y, delta z, still going to 0, 0, 0 of the double integral along the top plus the bottom plus the left plus the right, f dotted with n ds over delta x, delta x, delta y, delta z. Okay, so it would be the limit of actually the sum of all of these 6 things divided by things. I've just broken that up. I'm taking the limit over the front plus the back, plus the limit over all the other pieces. And if I were going to evaluate those, I'd actually break this up into 2 more, keeping the top and the bottom together and the left and the right together. I want to focus on just approximating this piece. Okay, so just focusing on the limit of this part, I can say that is now approximately the limit as delta x, delta y, delta z goes to 0, 0, 0 of, we approximated this way, f of x naught plus delta x over 2 y naught z naught times delta y delta z. Adding this is adding this. So minus f of x naught minus delta x over 2 y naught z naught times delta y delta z all over delta x, delta y, delta z. So I can just replace these 2 things with what I've approximated them as. Now, this is getting a little bit cramped. What I'm going to do is rewrite that limit, which is approximating the limit of these first 2 terms. I'm going to rewrite that a little bit bigger so that we can take a look at what happens when we evaluate that. So we've gotten the limit as delta x, delta y, delta z goes to 0, 0, 0 of f of x plus delta x over 2 y naught z naught times delta y delta z minus f of x minus delta x over 2 y naught z naught delta y delta z all over delta x, delta y, delta z. Now, in both terms on top, there's a delta y, delta z. So I can factor that out, and then I can see I'm going to be able to cancel it because there's a delta y, delta z on the bottom. So if I factor that out and cancel it, I'm going to have the limit as delta x, delta y, delta z goes to 0, 0, 0 of f of x plus delta x over 2 y naught z naught minus f of x minus delta x over 2 y naught z naught all over delta x. All right, now f was a function of x, y, and z. I'm going to think of the output of that as being a w value. If I hold y and z constant at y naught, z naught, I can create this plane where I'm allowing x to be the only input variable and w would be the output. So I'm looking in the plane, this would be a plane in 4 space, where I'm holding y fixed at y naught and z fixed at z naught. Okay. So 4 space, I've got 4 variables, x, y, z, and w. If I hold 2 of them constant, I'm going to get a plane. So it's going to be parallel to the xw plane. All right, excellent. So what's going on here with this basic limit here? Well, let's suppose that x naught was here. Then this would be x naught plus delta x over 2, and this would be x naught minus delta x over 2, because of course delta x, and therefore half of delta x, are positive numbers. Okay. And let's just suppose this is the graph of my function. This would be w equaling f of x y naught z naught. So that would be the curve that I get by holding y and z fixed at y naught z naught. So that's the cross-sectional curve that I would see for this particular function. Okay. Now, what this is actually calculating is a slope of a secant line. This right here, that's the difference between the w value here and the w value here. So that's the rise of that secant line. Delta x, that would be the length of this subinterval, because this is delta x over 2, and this is delta x over 2. So this is just rise over run. This is representing the slope of a secant line. Well, I'm taking the limit, okay? Now, delta x, delta y, delta z are all going to 0. There are no delta y's and delta z's in this formula. So for practical purposes, all I'm concerned with is the fact that delta x is going to 0. So as that happens, these 2 points are moving closer and closer and closer to x naught. Okay. So usually when we're working with secant lines, we hold one endpoint fixed and we move the other endpoint towards that. Here, we're doing something a little bit different. We're holding the point in the middle fixed, and we're moving these points closer and closer and closer and closer to that same point that's in the middle, but I'm still taking the limit of the slope of a secant line. And if I take the limit of the slope of a secant line, I'm going to get the slope of a tangent line. So I'm going to be getting the slope of the tangent line to this curve at x naught. But what's the slope of that tangent line? That's going to equal the partial of f with respect to x, because I'm making x my only input variable by holding y and z constant. This will be evaluated at x naught, y naught, z naught, which is the partial of f with respect to x at p naught. So, by looking at the limit of the flux over the front and the back divided by the volume, so the flux density, just taking into account the front and the back surfaces, what I get is the partial of f with respect to x at p naught. Now, I know that if I'm actually calculating flux density, I've got to take into account the left and the right, and the top and the bottom as well. Well, it shouldn't come as a huge surprise, having seen this work, that if I look at the limit of flux density over the left and the right, what I'm going to get is the partial of g, which is the second component function, with respect to y at p naught. And if I do the same with the top and bottom surfaces, I'm going to get the partial of h, the third component function, with respect to z at p naught. So I've just worked through a third of the derivation, but the remaining 2/3 are very, very similar. We just approximate by choosing the center point of each box. Okay? And when we do that approximation and then take the limit, it really does come down to, hey, I'm taking the limit of a slope of a secant line. Ah, gee, that's going to be the slope of a tangent line. And it just turns out that that's going to be a partial derivative because I'm holding 2 out of the 3 of my input variables constant as I work through this. Very cool argument. Very indebted to H.M. Shea and Divgrad Curl and all that. Highly recommend that book.